Good afternoon, one and all. Today we are having with us Dr. Nitin B. George, of Associate Professor in the Department of Electrical Engineering, IIT Gandhinagar. He took his BTech from TKMC in 2007 and MTech from National Institute of Technology, Rourkela in 2009. He had completed his PhD from Indian Institute of Technology, Bhubaneswar in 2012. He has many papers to his credit, and he is an alumnus. As an alumnus of this college, he is with us for the last 14 years. Welcome you, Nitin.
Yeah, thank you, Miss.
Over to you.
Yeah. So I think today's session, what I have planned is we will look into advances in array signal processing. So that is what is the topic which we are looking at. So what we are interested in is signal processing, but signal processing when we are handling array of elements. Array of elements means it can be array of sensors, it can be array of actuators. These are the two type of things which we are currently looking at, and how the signal processing will change when we go from a single element to multi-element, and from multi-element to an array. Okay, so that is what is the objective of this session. That is how it is planned. Okay, so primarily what we have worked on is we have worked on microphone arrays, but the type of algorithms which we will see, or which we will actually do in microphone array signal processing, can also be extended to antenna arrays with some modification. Okay, and maybe some other arrays maybe in the future. Okay, so let's get into the topic and try to understand what we are talking about. What we're talking about is an array. Array means we have a set of sensors which are arranged in a predetermined geometric shape. So that shape can be a linear array in which we could be having a set of sensors which are arranged in a line. It can be a rectangular array, it can be a circular array, it can be a spherical array, or it can be an array in which the sensors have been placed in some specific manner, which is not a very defined shape. Understood? So if you see this picture, this is a spherical array of microphones. Okay, so this is a circular array of microphones. We have a rectangular array of square array of microphones. Okay, so this in all these type of arrangements, we can have a uniform arrangement, or you can have a non-uniform arrangement. Okay, it is not absolutely necessary that we will have to arrange my sensors in a linear fashion, and also it need not be in a uniform linear fashion. What is uniform linear fashion means? You have a uniform gap between these sensors. Okay, I could have a situation where I can have first sensor here, second sensor here, then I can have third sensor here, maybe fourth sensor over here. This is also an array. Okay, this is the basic idea of what we are looking at as arrays. Okay, and here I have shown the example of microphone arrays. It could be a loudspeaker array, it could be an antenna array. These are very critical applications where we will go for antenna arrays, or we will go for microphone arrays, or we will go for loudspeaker arrays. Okay, so in this session we will also look at what are the practical applications of this, where in your life these arrays are coming. Okay, and what is the impact of that, and how the signal processing is to be done on or for an array. Okay, so this is what we are trying to see. So first, if you want to look at a simplified problem, I am taking here a linear array, an uniform linear array, where I have some sensors. So the first sensor is giving me an output which is equal to x1t. My second sensor is giving me an output which is equal to x2t. And I have a distance between them. The gap between them is given by d. Then I have several other sensors, and I have a total of m sensors, which we have arranged in a uniform linear array. So this is the term which we will use, ULA. ULA means uniform linear array. Now what is going to happen is, you have some source. Some source in the case of microphone array can be a sound source somewhere over here, which is going to generate some sound. Okay. Or it can be another transmitter which is going to transmit some signal, and this signal is going to reach the array. Suppose I have only one microphone in this situation. Okay, so what I'm saying is I have one source. So this is the source, and I have one microphone, which let it be somewhere over here. What are the limitations of having one microphone, and what are the advantages of having an array of microphone is what we are trying to look at. So if I have, the fundamental question is, if you had only 1 ear, what would have been the difference compared to currently when you are having 2 ears? Can I ask question to people there? Hello?
Oh, yes, sir.
Yeah. So is this, that camera is working or not working? This is better. Yeah. So if you had only 1 ear, what would have been the difference? Anybody? So currently you are having 2 ears. Suppose you had only 1 ear. How your life would have changed? Anybody want to answer? Yeah.
Interferences from different sources. If we have 2 ears, more than one pair of ears.
Okay. So suppose we had 2 ears and both were at the position of your eyes. How your life would have changed? Yeah, I think the person with the mic can answer. Yeah. Yeah. If you are having ears at the position of our eyes, what difference will be there?
The hearing experience would be different. Like having
Correct.
ears,
How hearing experience will be different?
like the sounds that reach like the sounds on those like ears are designed in a manner
Ah.
To get the like our it would be different from what we are currently hearing. Like
Correct. It would be different. What is the difference? It is different. Fine. What is the difference? Okay. Now I will give you a third situation. So you have 2 ears and you have a head in between. Your head is there in between. Okay. So if your head was transparent to sound, what difference would have been? So currently we have a very nice situation where you have 2 ears on 2 different sides, and in between you have a head. Your head, this head only. Okay. So there is a head in between and you have 2 ears. So suppose there was no head. How your hearing would have been different? Question is not clear?
can you ask again, sir?
So suppose the ear is at the same location. Okay. But there was no head. So assume that there is no head, only 2 ears are there. How your hearing will be different?
The hearing would be staying like
Okay.
ears are in the same position.
Same position, then there is no head. You don't have a head. There is only, you assume that there is only 1 year here, 1 year here, and there's no head in between.
So, do I have to answer this question like biologically?
No, no,
You-
biologically. You can answer it from a signal processing point of view or an electrical engineering point of view. What difference would be there?
The positions being same.
Same.
I think it would be the same as like yes, I'm the same position now. So
Okay.
there won't be much of a difference.
Fine. I think that will give the motivation for why we need array signal processing. Okay. So what change would be there? This is last question on years. Okay. What difference will be there? The only difference is if somebody is calling you from the front or from the left or from the right, you will have no idea whether the person called you from the left or from the right. You will have no sense of directionality of the sound. Because why? Because why? Why you will not have no sense of directionality? Because I have a microphone over here, which is your 1 ear, and we have source over here, the signal I am getting over here. If the distance is same, even when the source is over here, I have the distance equal to same. Even when the source is over here, I have the distance is equal to same. Correct? Because all the distance is equal to the same, I will have no clue whether somebody called me from the front or from the left or from the back or from the right. So you will lose your sense of directionality if you have only 1 ear. Okay. So what is the beautiful part? The beautiful part is you have 2 ears and a head in between. Okay. What is the head doing? What is the head doing? The mic is still with you, no? Yeah, you can answer.
Actually, the as you said, the head is acting as a platform for the ears. So actually, it helps in crossing and understanding the direction. Like
So the head is creating a barrier.
Yeah.
Okay, it is like a wall in between two sensors which are kept on the left and kept on the right. Correct? Now, if somebody is calling you from your left from your right side, what is going to happen? The sound will first reach the right ear. At the same instant, the sound will not reach the left ear. The sound will reach after a different delay. It will reach the right ear. And the head is making sure that there is more delay for the sound signal to reach your left ear. Correct? Now what has happened? Now my brain is able to understand. I am able to understand there is one signal which is coming, but the magnitude of both the signals are different at both my ears. And now I am able to estimate the direction of arrival of the signal. Okay, so by going from one sensor to multiple sensors, so where in your life we have array, sensor array, your ear is a sensor array. One sensor here, one sensor here, you have an array of ears, you have an array of eyes also. Okay, so I have now created a primary motivation for us to think of systems in the sense machines having array of sensors rather than single sensor. Okay, so what are the advantages which arrays of sensors are going to give me compared to one sensor? Okay, so what is the system or the machine I am looking at? The machine can be your mobile phone, the machine can be your laptop, machine can be your iPad. Okay, the machine can be your Amazon Echo, the machine can be any of the devices which we are interacting with on a day-to-day basis. All of them can sense a lot of information if I have a sensor array compared to a single sensor. Okay, so we can say that is the primary motivation with which we are going to start. So that's where I wrote direction of arrival estimation. So if I want to estimate the direction of arrival, and if I want to estimate the direction of arrival accurately, I may need an array of sensors. Okay, any doubt on the motivation part? Clear? You don't need to transfer the mic. You can say.
Yes, sir. It's clear.
Yeah. You keep the mic there only. Okay. Yeah. Fine. Now what to do? Now, what we are going to see is what are we talking about? Okay, because we are interested in machines listening to us. Okay, we have to do a little bit of machine listening, and we want to understand how our arrays are going to help us. Okay. So now I'm going back to my earlier whatever explanation which I was giving. So I have a first sensor array. Sorry, first sensor. I have a second sensor. I have M sensor. Each of them is giving me an output. Okay, each of them is going to give me an output. Okay, fine. Now what to do? Now what will happen? Because I have a finite distance between the first sensor and the second sensor and the third sensor, and the third sensor and the M sensor, what is going to happen? What is going to happen? Yeah, that it's muted. Yeah, what is going to happen? What is going to happen? So there is a finite delay between the signal which is reaching the first sensor and the signal which is reaching the second sensor. How much delay will be there? How much delay will be there will depend on what is the wavefront which is going to reach the sensor element. Okay. So if I have a near field source, typically I will have a spherical wavefront. Spherical wavefront means what? You will not have a planar wavefront, you will have a wavefront like this, correct? But now if you are looking at a far field source, what you can assume? You can assume that we have a plane wavefront. So in this diagram, what I am doing is I am assuming that my source is a far field source and I am having a wavefront which is a plane wavefront. Okay. So this line I am assuming is the plane wavefront. So what happens? At some point of time, this wavefront will reach the first sensor. After some delay, it will reach the second sensor. After some more delay, it will reach the M sensor. Okay. Now, can I use this information to identify from what theta the source is coming from? That problem is what is called the direction of arrival estimation. Okay. Then there is a second related problem, which is called source localization. So the first one, what we are looking at is DOA estimation. Second one is called source localization. Source localization means you are estimating the direction. Means you got from which theta your sound or your signal is coming. But we should also estimate in what range is this source. Means it's as if in depth estimation. Okay, where we should be able to say, if I am a device, if I am putting a device in my room, I should be able to say from which direction the sound came and at what depth in that direction this sound came. So I am able to localize the position of the source of the signal. Okay, that is what is known as source localization. Okay, so first we have direction of arrival estimation, and second we have source localization. The third term we will listen very, very frequently is what is called as beamforming. Okay, so you have heard beamforming sometime earlier. Somewhere you have studied beamforming. Yes. You can yes or no. Beamforming?
No, sir.
Okay. So beamforming we will it's a very old thing only, but now it is becoming very popular. Okay, I will give you some case studies on some products where beamforming is becoming popular so that you will get a sense. So beamforming means, suppose I have identified that this is the direction from which my desired source is speaking. But there are some other people who are speaking from here, which I don't want to disturb my system. What I could do is something called beamforming, in which I could create a beam in the direction of the source. And I can create a null in some other directions where I don't want the signal to be sensed. So by manipulating the beam, or by manipulating the radiation pattern in case of an antenna or a microphone pickup, I will be able to first identify the source and then change the beam pattern electronically and pick sounds from a particular desired direction and avoid sounds from some other direction. Okay, this is the basic idea of beamforming. So these are the three major areas of research in array signal processing. One is you estimate the direction. Second, you localize the source. Third, you do beamforming. And when you do source localization, what you also do is you will also estimate how many sources are there. Because initially I said there is one source, but there could be multiple sources. So the number of sources which can be localized is actually dependent on, in the basic algorithm, it is dependent on the number of sensors. Okay. So if you have more sources than number of array elements, it becomes difficult in a traditional approach. And then we have something called other methods are there where we can have less number of sensors and we could identify more sources. Okay, let's not worry about that. So currently, the only thing we have to understand is we have something called an array. Array is where sensors are arranged in some shape. Shape can be uniform or non-uniform. These are some of the examples. And then we said we have to understand what is the source. What is it, a near field source or is it a far field source? What type of wavefront is going to be whatever wavefront will we be dealing in our problem. These are the main things which we'll have to understand. And then we said we will look at direction of arrival estimation. We will look at source localization and we will look at beamforming. These are the three major things which we will understand. So if you want to little bit understand mathematically this problem, what is written over here is the same diagram. Whatever diagram I had shown earlier, exactly the same diagram is there, where you have M sensors, 1, 2, etc. M sensors are there. And you have some source. It's a single source problem. So there is some sound which is reaching here. There is some other sound which is reaching here. There is some other sound which is reaching over here. So you are getting how many outputs at a particular point of time, even though you have only one source. I have one source and I have an array element. Okay, element of M sensors are there, M microphones are there. So each microphone is going to give me an output. First microphone is going to give me an output, and M the microphone is also going to give me an output. Okay, so that is what we have writing in this vector. Okay, what is this vector? This vector is the sensor output. X1 is the first sensor output, X2 is the second sensor output, and Xm is the M the sensor output. Okay, how many source signals are there? There is only one source. There is one person speaking. Okay, that signal, let us assume that this signal is equal to ST. ST is what? ST is the original signal which is there. Then what we are writing is the signal produced by the array elements, if it is a uniform linear array, is given by this ST multiplied by this matrix, this vector, which we call the steering vector. Okay, so I have a source, single source, which is equal to ST, and then I have a vector which is equal to the steering vector. And if you look at the steering vector, it has a variable called tau. What is this tau? Tau is the time delay between the signal reaching at the first sensor and the second sensor, or the second sensor and the third sensor. That is called tau. which is given by this. What is d sine theta? D sine theta is the difference in length. This one is called d sine theta. Okay. So, and this n vector is the noise vector. Okay. So what I have done is, I am saying I have one person talking in the room, or there is one source which is there. Okay. And that signal is picked up by not one sensor, but now by an array of sensors. There are m sensors picking the signal. So I can write the array output as a s into some vector plus some noise vector. Okay, this is a simplified representation of what we are looking at in an uniform linear array when you have a single source. Okay, so if I have a source and if I have an array element, what are we measuring? We are measuring what is the output of the microphone or output of the sensor element. So what is available with us is X, because X is something which can be measured. Okay, so I am deploying a sensor array, and using the sensor array, I am measuring something. Now the question is, by looking at the measurement X, will I be able to estimate tau? And from tau, will I be able to estimate theta? Can I estimate? Because this is tau, and that is dependent on d, and that is dependent on the speed. These two things are fixed because I have created the array. So I know what is the sensor gap between the sensor elements. So d is known to me. So indirectly, I will be able to measure the theta. Okay. So the direction of arrival estimation problem. What is the problem? Problem is you have X is equal to S into something plus N. Okay. So that is our problem. And from there, I will have to estimate. So I can write in a general form. I have X, which is a vector, which is equal to A, S plus N. Okay. That is what is our situation. And I need to find out this A. If I am able to find out A, I will be able to find out what? If I am able to find out A, I will be able to find out tau. If I am able to find out tau, I will be able to estimate the theta. Okay. This is when I have one source. Now, if I have multiple sources, what is the case of multiple sources? Multiple sources in the sense, I have again 1, 2, etc. m array elements. But there is one source which is coming at theta 1 angle. There is another source which is coming at theta 2 angle. A third source which is coming at theta k angle. Everywhere we are assuming that the sources, this is far field. Okay. So that assumption is there. This source is far field and the wavefront is going to be plane. That is what is the assumption we are taking over here for the time. Okay. Now what happens is the earlier vector which we wrote. What was the vector which we wrote? We said S multiplied by some vector plus some noise. Okay. So I'm taking the first element as 1 because my reference point is the first element where we are assuming that there is no delay. It is starting from there because I am not interested in depth estimation. I am only interested in the theta. Okay. So I can ignore the what you can say, I can start my reference point can start from the first sensor itself. Okay. Now, if I go for multiple sources, what happens is each source has some theta 1, some theta 2, etc. theta k. So each source will create what? One vector, which is the steering vector. Like that, how many such steering vectors are there? K such steering vectors are there. Okay, so one source is creating one steering vector. Second source will create a second steering vector compared to the array elements, m elements. And similarly, I am going to have k such steering vectors. And this entire thing will become something called a steering matrix. Okay, so what I can write? I can write now that the x vector is equal to as plus n, where A is the matrix. A is a matrix now. Okay, earlier it was a vector. This is called a steering matrix, which contains, this is a collection of steering vectors. Okay. Now the question is, will I be able to estimate A given X? Okay, under some condition. So that is actually the direction of arrival problem. I am not going into that right now. This is just to give a motivation about what is the approach. So normally what we can do is we can do a singular value decomposition, and then we will be able to get an estimate of A under some condition, and then we will be able to estimate the theta. Okay, so that is not our objective. Our objective right now is to understand the motivation behind array signal processing, why array signal processing is needed, and what are we actually doing when we are talking about direction of arrival estimation. Okay, any doubt till now? Is it clear? Clear? Okay, fine. Fine. If some doubt is there, you can ask now. Any doubt? No. Okay, fine. Okay. Now let's take an example of a example where we will look at how an array signal processing can solve the problem in a better way compared to an adaptive signal processing problem. So first I will explain the adaptive signal processing solution to the problem. And then we will look at, can I have an array signal processing solution, which could be a better solution compared to the adaptive signal processing problem, which we are looking at. Okay. So the problem which we are looking at is what is called acoustic feedback. So what is acoustic feedback? Acoustic feedback means this is a simple diagram of a hearing aid. Okay. So what I have got? I have somebody who is having a hearing loss. So what is the hearing loss? Hearing loss means you go and you do your ear test, you do an audiometry, and you get a hearing profile, some hearing profile you get. Okay. Hearing profile, this could be the hearing profile of a healthy person. Where? What is the meaning of that? This is frequency versus amplitude. The meaning of this is, if I have an amplitude for this frequency 500 Hertz, which is more than this A1 level, you hear it. Okay, if the amplitude is less than A1 level, you don't hear it. Now, suppose you have hearing loss, what can happen is, you can have a different curve compared to a healthy hearing curve. So now what is the situation here? For 500 Hertz, earlier, if I was having an amplitude of A1, I would have heard the sound. Now, because my hearing profile has changed, or I have a hearing loss, I can hear 500 Hertz only when the amplitude is A2, not at A1. Okay. And this could be different for different frequency. There could be some frequency, suppose this is 2K, where I don't have any loss, I don't have any problem. So what is the simplest solution to the problem of hearing loss? Simplest solution could be, you could think of a hearing aid. What a hearing aid will do? Hearing aid will amplify the sound and play it to a loudspeaker in the simplest, crudest form. But it is a frequency specific amplification, and it is a user specific amplification, because your hearing loss is not equal to somebody else's hearing loss. So for every person, there should be a user specific amplification, or a user specific gain has to be done. Okay. So in the simplest form, what I will have mic, which is going to pick the sound. Then I will have some DSP unit. Here I have just mentioned DSP unit because it will be needed for some other application. We can assume that it is just amplifying for the time being. Then I play it through a loudspeaker, and the amplified sound will reach the ear. So we are assuming that everything is going to be happy because you have amplified the sound, and the amplified sound is reaching the ear of the person who is having an impairment. Now the problem is, if you look at a typical hearing aid, what type of hearing aids are there? You have something called behind the ear hearing aid. You have in the canal hearing aid, in the ear hearing aid, different types of hearing aids are there. But most of them, the problem is this mic and this loudspeaker are very close to each other, because you cannot keep, can I keep the mic over here on my glass in the front at the middle for my hearing device? Is it a good idea or a bad idea? Because I need to amplify the sound, I need to pick the sound. Can I now put the microphone in the middle of my glass and then connect that to the hearing device? Because now if I do that, what is the advantage? My mic is here, speaker is here, there will not be any feedback. Okay, what is the feedback? Feedback means the amplified sound, in addition to going to the ear, can also be picked up back by the microphone. Okay, so what happens? The microphone is picking up not only the hello which I am saying, but also the amplified hello which I said little bit earlier. And the amplified hello will be further amplified, and you will hear this beep sound. Like if you take that microphone in your hand and go and keep it near the speaker, what happens? There will be a whistling sound. So what we normally do to solve the problem? Somebody will run and reduce the amplification, the gain will be reduced. But I am putting a hearing aid so that somebody is not able to hear. So reducing the gain is not a solution. Second solution is you can run away from the speaker. That is also not a solution here. Why? Because this is a fixed device. Okay. This is the problem. What is the problem? So I have a solution, which is the hearing aid. I created something, and now I have created a new problem, which is called acoustic feedback, where the microphone is not only picking up the sound of the speaker, but also the amplified version of the speaker, which has been already played by the loudspeaker in the hearing device. Okay, this is the acoustic feedback. This is not very good, because the problem is, if I have feedback, I will mostly be listening to this whistling sound, and I am not able to understand what conversation is going on. So that is a very major difficulty in a hearing device or a hearing aid. So what could be the solution? Yes. What could be the solution to the problem? Can there be any solution? Can I put a filter and remove the feedback? Yes, sir. Mic is still there now. Try. Means my question is that your this microphone is picking up some signal. Can I now put a filter, FAR filter, suppose, and then there is a gain, and then it is getting played through the loudspeaker, and this is the feedback, this is the speech or some signal. Can I use an FAR filter in such a way that the feedback signal will not go beyond this FAR filter? Can I do that?
Yes.
Okay. So we cannot do that. Why we cannot do that? What type of filter will we create there? What type of filter we will create there? So the problem is the desired signal and the noise or the signal to be cancelled, both are speech. Both are hello. So they have the similar spectral characteristics. Correct? Correct? So your signal and noise are having the same spectral characteristics or similar spectral characteristics, and both of them are occurring together at the same point of time. So normally, when we study filtering in normal DSP, what we will do? We will say, I will design a low pass filter. What is the meaning of that? That you have frequency and you say, I will create a filter like this, where frequencies up to here F1 will be passed. After that, I will reduce, attenuate. That is what we normally do. But here, what is my problem? Because there I know that this is signal and this is noise. So I have a difference in the spectral domain of signal and noise, and now I am able to apply a filter. But in this problem, that is not possible because my signal and the noise both are in the same spectral region. So what to do? So now FIR filter is a bad idea. FIR filter will not be of any use because FIR filter will remove the hello which somebody is saying also, because all of them are within the stop band of the FIR filter. So what is the solution? So that is where we could look at adaptive filtering as a solution to this problem. Okay. What happens in adaptive filtering? What happens in adaptive filtering is, so this is a simplified block diagram where I am saying that I am going to do a feedback cancellation. What is feedback cancellation? I have a desired signal which is picked up by the microphone and it is going inside the hearing aid and it is played by the loudspeaker. And this will go to the ear of the person. Now you have a signal which is fed back that we already discussed. That is called the acoustic feedback. Okay. Now, what we are looking at, what the possibility which we are looking at is, can I tap the signal from here, pass it through a filter, and subtract that from the output of the microphone? What I'm trying to do, you have a microphone. Microphone contains desired plus feedback. Now what we are saying is, can I, from the sum of this, can I subtract an approximation of F so that you get an approximation of D at the output of the adder? That is what we are trying to do over here. Okay, so the question is, I have D plus F which is coming from the mic. I don't want F because F is the feedback which I don't want to keep. I cannot use a normal filter. Now, can I magically create F cap such that D plus F minus F cap will give me D cap? This is the problem. So, under what condition this will work? Under what condition can I create F cap? I can create F cap if the characteristics of this path, okay, if the characteristic of this path from here until here is similar to this from here until here, or this filter I have written over here as adaptive filter, suppose it is FIR filter. If the characteristic of this filter, if the behavior of this filter is similar to the upper blue path, or the transfer function is similar to the upper blue path, now what is going to happen? So I am creating a feedback from here until here. The same input signal is passed through a model of that path. Okay. A model. Model means what? A model is a transfer function of a physical system. So you have a physical system, which is the loudspeaker, a path, an air path, and a microphone. That path is modeled by an FIR filter, which we call the adaptive FIR filter. And if the behavior of the lower path, which is the adaptive FIR filter, or the characteristic or the transfer function is similar, then I can theoretically do this cancellation where from D plus F, I will be theoretically able to subtract F cap, because F cap will be similar to the upper path, because we are trying to indirectly model the acoustic path, the feedback path, the upper blue path with an adaptive filter. Okay, any doubt? Is it clear? Okay, fine. Now, what happens in the modeling? Because that we will have to understand, because that is the most fundamental thing in adaptive filtering. Okay, what is the most fundamental thing in adaptive filtering? Most fundamental thing is Most fundamental thing is, now earlier from that problem where we are saying is, if I have a model of the acoustic path, then that filter I could put here. If I could put that filter here, my problem can be solved. Okay, that is not how in real life it happens. This is happening online, but here I am trying to simplify the problem. Where we are saying we have an acoustic path. We want to create an FIR filter which is going to behave like that path. Okay, the characteristics of which will be similar to that of the acoustic path. That is what is our objective. Now, how we can do that? What we can do is we can use an adaptive filter. What adaptive filter will do? So I have, this is ADC. Okay, so I have a physical path and I have a model path. I generate some input, give it to the physical path. Physical path will give me some output which is equal to D. The bottom path, which is an FIR filter, which is an adaptive FIR filter. What is adaptive FIR filter? Adaptive FIR filter means the multipliers, the coefficients in the FIR filter can be updated. That is called adaptive FIR. Okay. So when I am giving an input X of n through the upper path, you get some D. When you give the same input through the lower path, you get some output Y. If I can somehow make D as close as possible to Y, then what I can say, I have created a very nice model of the acoustic path. This is the modeling problem or the system identification problem, which we are indirectly trying to do in the feedback cancellation also. Okay. So what we are saying, you have a physical path, then you have a model path, and we update the parameters of the FIR filter, which are the multiplier values, in such a way that the response of the upper path is as close as possible to the response of the lower path. Or what E is the difference between the upper path output and the lower path output. Okay. And what is the lower path output? It is A transpose X, which is coming from here. This is the X vector, A vector, and you get the output. Understood? So now in an adaptive filtering problem, what we try to do? We try to say, if I can somehow minimize a function of E, minimize it, I may be able to get D as close as possible to Y. Okay, I may be able to get D as close as possible to Y. Under that condition, what is the value of the A vector? That filter will be equal to the model of the path. Okay, that filter will be equal to the model of the path. So if I simplify it, this is standard adaptive filter problem. Okay, if you have done any adaptive filtering course, you would have seen the exact same. Okay, where we say what? Where we define a cost function. Here I am taking expectation of E square as the cost function. Okay, what is that expectation of E square? Where this equation 3, I am taking square. So I am having D square minus D plus this. Then once I do all of those things, what I will finally get is, I will get this equation. What it is saying, that I have a cost function, which is what? Some A square plus A plus something. Okay. So it's a quadratic function of A. What is A? A is the filter weights. Okay. So if I have a quadratic function, how it is going to look like? It could look like a parabola, or it could look like a paraboloid when you increase the dimension. So I could find out under what condition you will get the minimum value of the cost function. That can be found out. This is standard adaptive filtering problem. If you do that, what you will see is that the optimal value is equal to R inverse P. What is R inverse P? R is this I will explain with an example, then it will be clear. So what I am saying is, the optimal weight value is dependent on P, which is the cross correlation vector, and R, which is the autocorrelation matrix. Let me go to the diagram and I will explain it very clearly. So what I am saying is the optimal value is equal to R inverse P. What is P? P is the cross correlation between X and D. Okay. What is P? P is the cross correlation between X and D. What is the meaning of cross correlation between X and D? How correlated is X and D? That is the indirect meaning of what is hidden inside P. What is P? P is the cross correlation. Now, suppose let's assume that I have a barrier over here. Okay. And this microphone is picking up some sound, which is a noise, which has nothing to do with X. Okay. Now, if I find out the cross correlation vector P, what will be P? What is P? P is the correlation between X and D. Now, what I have told that I have a barrier in between. So D has nothing to do with X. D has something to do with noise, which is uncorrelated with X. Okay, you're getting it or not? Okay. So I have an X. X is producing the sound from the speaker, but X is never reaching the microphone. Microphone is picking up something which is nothing to do with X. Now what I can say? Now what I can say is this P will be a 0 because there is no correlation between X and D. X and D are uncorrelated. If it is uncorrelated, this P will be 0. So this W will be 0. W will be 0 means what? This FIR filter will have 0 multiplier values. Or this output will be 0. Or the error will be equal to what? Error will be equal to the noise. Okay, error will be equal to the noise. So what I am indirectly saying is I can model what? I can model only signal components in D which are correlated with X. This noise is not correlated with X, so it cannot be modeled. Okay, it cannot be modeled. So this is the basic idea. This we have used in, if you look at any standard adaptive filtering book, they will do a lot of examples in which this can be explained very nicely. Correct? For example, I will give one simple example. If you are having a mobile phone, you have two microphones, suppose. This is the first microphone into which you are speaking. So this microphone will pick up speech plus some noise. And I put another microphone behind my mobile, which is M2. M2 will pick some version of noise, which is not equal to the same noise, but it is similar to the same noise because both the noise came from the same source. Now, can I design an adaptive filter to do denoising? Can I design an adaptive filter to do denoising? I can easily design an adaptive filter to do denoising. What I will do is I have M1 signal, I have M2 signal, I will pass it through an FIR filter. The output I will subtract from here and I will use that to update the FIR filter. Now what happens is, what FIR filter will try to do is from speech plus noise, I will try to remove whatever signal component is correlated with M2. What is the signal component in speech plus noise which is correlated with M2? The noise component. The noise component will reduce, or we will be able to do a denoising. Okay, this is the basic idea of adaptive filter. Okay, any doubt? No doubt. Okay, fine. Now this is an adaptive filtering solution. Now can I have an array signal processing solution to the exact similar problem? So this is a 2019 paper where instead of having one mic, which we discussed in the earlier problem, I am having multiple microphones within a single hearing device. Okay. So I have 1, 2, 3, 3 mics I have put. So somebody will be speaking from here. That speaking will be there. This will be amplified. And this is the hearing aid amplifier, you can say. And it will be played through the ear. And it will also be picked up by the microphone. Now, what in this paper they are trying to do is they are trying to do something called a null steering beamformer. Null steering beamformer means instead of 1 mic, I have now 3 mics. And I have a, this is the speaker. This is the original speech which is there. Now I can create a beam in the direction of the speech and a null in the direction of this somehow. Somehow means actually we can do it. So by introducing what? By introducing an array of elements. Okay. So our original problem, which we saw over here, had 1 microphone, 1 loudspeaker, and we have the feedback problem. We try to do a signal processing solution to that. But what happens is, if you read it properly, it will say there is a problem of bias which is going to come. And so this solution is not a very good solution. Okay, because there is some correlation, finite correlation between the signal and the noise. Okay. But here what we are saying, the same problem, I am now formulating the problem as an array signal processing problem, where instead of 1 microphone, I am deliberately putting 2 other microphones and creating an array signal processing problem where I could do something called a spatial filtering. Okay, how many types of filtering we have seen? We can do a frequency domain filtering. We can do a time frequency domain filtering. Then we saw an adaptive filtering. Now we are saying spatial filtering. What is spatial filtering? Spatial filtering means I can define from which direction I want signal to be picked up and from which direction I don't want signal to be picked up. That is called spatial filtering. Okay. If I give an example, now I am speaking, there is some speaker over there, and everybody in the room is listening to me. Can I create a system where only one person is listening to me and others are not able to hear me? Can I do that? Yeah. Can I do that? Yes or no? Yes or no? Or don't know. Third option is don't know. Problem question is clear? Is the question clear?
Yes.
Question is, you are not going to use any headphones. Some sound is going to be played in the room, but only you will listen to that sound. Others will not be able to listen to that sound. Is it possible? It is possible. Okay. So where we are creating directional sounds. Okay, where we are going to have a directional sound, a beam in your direction only. Understood? That can be achieved by arrays. That can be achieved by my loudspeaker arrays. In this problem, I am having a microphone array where we are trying to pick signal from the environment. So I can pick signals of, even though all of you start speaking, suppose all of you are starting speaking, but I want to only listen to one person. Can I do that? Yes. Because my array can be told that you pick sound only from one person and you can ignore everybody else. So what I should do? I should create a beam in the direction of that person from where I want to listen to, and I should create nulls in the direction of other people who are creating noise. Okay. So by creating that, so finally what is going to happen is, you will have mic 1, you will have mic 2, you will have mic 3. This output I will take I will do some multiplication. I will add them together and I get some output. But these multiplier values W0, W1, etc., Wm minus 1, I am going to adjust in such a way that I pick sound from a particular direction and I don't pick sound from some other direction. Or I am going to estimate what is the W vector. So this structure is looking very familiar because this structure is looking like an FAR filter. So this is actually an FAR filter, but instead of a normal filtering where we are looking at frequency domain, we are doing spatial filtering. Okay, so that is what is the meaning of spatial filtering and how array is going to come and how beamforming can come in the same problem where we already tried to solve using adaptive filtering. Now the same problem we are trying to solve using an array of sensors and bringing in the concept of beamforming into that. Okay, clear? Any doubt? Fine. Okay, so let me take two real life examples so that you get a sense of how these algorithms will come. This is fine. This is just a setup to measure the algorithm, to test the algorithms. So this is an Apple HomePod. So this is like the Amazon Echo. Okay. So what it has got? It has got an array of 6 microphones. Even your Echo has array of, I think 5 or 6 or 7 microphones are there, correct? Why do we need so many microphones? Why do we need so many microphones? Your MacBook now comes with, I think, 3 microphones. Your iPad now comes with some 3 or 4 microphones. Everybody is saying, I am going to have array of microphones. Why? Because now I am able to do a lot of information gathering using an array, where I will be able to know whether this person is speaking from here or from here, whether there is a fan noise which is coming from here or here, whether I should play, because the question, the Alexa call came from this direction, which is noisy, should I do something differently? All of those decisions can be taken by putting in array elements, sensor arrays. So if you see this diagram, in this picture now, you can see here they are saying that they have a 6 microphone array. So this one device has 6 microphones. Then they are saying there are 7 tweeter arrays. So it's like a speaker array has been created. So by having a loudspeaker array, you are able to give directions saying that the sound can go high amplification in this direction, stereo in that direction. All of those type of combinations can be done. Okay. So what it says is you have an array of microphones, you have an array of tweeters, and you can create multiple beam shapes and sizes in this. Okay, this is an actual product. HomePod. Now, if you think of an entirely different problem, that is 5G. Okay, what happens in 5G? What is the difference between 4G and 5G? Other than bandwidth and speed and all those things. What is the major difference? Major difference is we are going for, if I use massive MIMO as a technology, I am going for an array of sensors or an array of antennas. Okay. Earlier we were talking about array of microphones, array of loudspeakers. Now here we are saying an array of antennas, antenna arrays. Okay. So in a cell, this is our standard cell. Earlier, if we were creating a beam pattern, which was like an uniform type of a beam pattern, now I can have multiple beams created within a particular cell targeted at even individual users. Okay, where I can have different bandwidth in different beams, and so many other things can be done. Okay, so this is the Samsung's massive MIMO system. Okay, where they are saying that they create a sensor array, and then they will be able to create an active antenna system. What is active antenna system? What is the meaning of active antenna system? So this beam pattern is not fixed. This beam pattern can be updated. Okay, this pattern need not be looking like this flower. It can be a different set of flower. It can be having 3 lobes, 4 lobes, 5 lobes. All of those things we can achieve by doing what? By doing beamforming, or by doing this spatial filtering operation. Instead of mic, I will put an antenna here. Okay, instead of mic, I am going to put an antenna over here. So that is the type of capability that array signal processing is going to give. Okay, now if you look at the same example only, you see, this is our current antenna setup. Okay, where you have a tall building, you have so many users which are there, everybody is going to get the same type of signal. Now when I go for a massive MIMO, what I am able to do? I am able to create beams. I am able to create beams for either individual users or group of users, and also move it, see, vertically and horizontally. So I will be able to have, even though I am using a large number of sensors, by using the concept of array signal processing, you will be able to have a better experience for our user, because we have more control on what type of beam, in which direction beam is going to go, what type of bandwidth can be given to this user, not to that user. All of those type of capabilities can come into an array signal processing. Okay, so here we are looked at 2 types of examples. One, we have looked at a speaker array and a mic array example. Similar thing will come in the Echo, or in your laptop now, or in your mobile phones now, or in your iPad now. Everywhere you look for, they will say 3 mic array, or 4 mic array, 5 mic array, and they will use this word called beamforming. 3 mic array with beamforming. Okay, if you go to MacBook specification, if you see, it will say 3 mic array with beamforming. Okay, and this concept has been all for maybe tens and tens of years, is used in ultrasound. Okay, what they do in ultrasound? You have an ultrasound probe. What is inside an ultrasound probe? You have a array of elements, array of what you can say, elements which are used for the doing the ultrasound. Okay, then we looked at a 5G application where an antenna array is going to be a very crucial part of 5G, and we need a signal processing for that, where we will do again an array signal processing. Okay, fine. And I think I am almost done. Fine. Okay, so these are some of our 2022 papers. If you are interested, you can read it. There you will get the actual math of it. Actual math of it is too complicated for me to understand and explain. Okay, fine. Yeah, any doubt? Any doubt anywhere? Clear? No doubt? Fine. Yeah. Then let's stop.
Yeah.
Okay. 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 Thank you.
Thank you, Dr. Nidin.
Yeah. Thank you.
Sir, that was a very interesting session. And
Yeah, thanks.
actually, we don't know much about array signal processing, but you started from the very base and made every examples very clear. And I express my sincere gratitude to your session. Thank you, sir.
Yeah, thank you. Thank you. Okay.
O-
Okay.
Okay,
bye.
thank
Bye.
you, Dr. Nitin, for your informative session. We are extremely glad to meet you here. Next time, please come
Yeah,
to
sure.
our college directly.
Yeah, sure.
Okay,
Okay. Bye.
okay, thank you, sir. Okay, thank you.